So we check for another test, and we have the limit comparison test. Limit comparison test. It states, suppose that you have two series. Keep in mind, you're going to only be given one of those. You're going to come up with a second series. But those series consist of only positive terms. A sub n and B sub n are both positive. If I take the limit of the sequence part and I get a number, that number is finite and positive. Well, if it's negative, that means one of them is negative and you messed up. You can't use this test if you get a negative number. But if this number right here is finite, it's not infinity, then either both series converge or both series diverge. Well, we need to work backwards. That is, we need to look at how do you take the limit of the ratio of two functions and get a number. Limit as n approaches infinity. I don't know if that rings a bell. That's called horizontal asymptote. And for the horizontal asymptote to be an actual number, the degree of the top and the degree of the bottom must be the same. If you recall, when we did the rational functions, graphs of rational functions, when we compared polynomials, and by now, since you've taken calculus, you've seen different types of equations that behave the same way, and number 18 is the first. So again, they're going to only give us one series. That's it. One. We have to come up with the second on our own. So this is number 18 that we attempted last time, and it didn't work. The comparison didn't work. The bigger diverged, or the smaller converged. So to guarantee this case, to guarantee that you're going to get an actual number, what we're going to do, we're going to create another series. And the series that we're going to create is going to be number free. That is, we're going to look at the top, say, okay, what dominates the top? A 2. What dominates over the denominator? Radical n, as n grows. So 2 over n converge. That's a sequence. Be careful. So if you look at the series, you could say that is the series from n equal 1 to infinity, 2 of 1 over n to the 1/2. Okay, now by choosing this, I know when I take the limit as n approaches infinity, I already know this. And in any order, it doesn't matter. Divided by 2 over radical n. Since I chose it to be dominating, I know that the ratio is going to be positive and it's going to be finite. So I know the limit is going to n approaches infinity. This is 2 over radical n plus 2 times radical n over 2. And the n's cancel out. And I'm looking at the limit as n approaches infinity. Two options, L'Hopital, or you divide by the highest power term of the denominator. Therefore, both what? We came up with a series. We don't know whether this converge or diverge, but the series that we got, we better know whether that converge or diverge. Isn't this a P series? Isn't this series here P equal 1/2 less than 1, therefore diverge? So therefore they both what? Diverge. Even though I cannot figure out whether this series converge or diverge, by getting rid of the number, I really got it to be the P series, and that's what's going to make the P series really useful. Now, if I was to take the limit as n approaches infinity, if I was to get infinity, that means I chose one of those to be bigger than the other. Or if I was to get 0, depending on how you divide this, right? So if I get a finite number, that means I chose correctly. Now I'm going to erase all of these arrows and cluttering and all that stuff. There it is. And that's how it works. By what? By the limit comparison test. I added an example. Let's look at that example. Again, if I look at this, if I use the comparison test, if I say n to the fourth plus 4 and n to the fourth, this is bigger for sure. 1 over will switch the order. n3, n3. This is 1 over n. But I know this diverge, and isn't that bigger? So no need to waste my time and do all of that work and then say, you know what, it didn't work. Instead, well, look, I have an easy way of eliminating the numbers. The top is dominated by n cubed. The denominator is dominated by n to the fourth. This is 1 over n. Again, you guys, 1 over n converge. That's a sequence. You must add the series in front of it. This is p equal 1 diverge. Or you could use harmonic. And now you have to show the limit. The limit as n approaches infinity of n cubed over n to the fourth plus 4 divided by 1 over n is going to equal the limit as n approaches infinity of n cubed over n to the fourth plus 4 times n over 1. That's the limit as n approaches infinity of n to the fourth over n to the fourth plus 4. You could use L'Hopital once. You could divide by the highest power term of the denominator. I'm going to use L'Hopital since it's only once. 4n cubed over 4n cubed. That equals to 1, bigger than 0. Therefore, they both diverge by the limit comparison test right there. And that's my conclusion. Now, if I could use the comparison on this, but since there are too many things to worry about, I'll just worry about dominating. What dominates the top? The top is dominated by n squared. How about the bottom? N to the fourth. That's really a shortcut. Comparison is quick, but if I have to get rid of so many terms, that's a lot of work. 1 over n squared, the series of that. P equal 2 bigger than 1, therefore it's a convergent P series. Now, the limit as n approaches infinity of n squared plus n plus 1, and this gets old really quickly. Divided by 1 over n squared, that is the limit as n approaches infinity of n squared plus n plus 1 over n to the fourth plus n squared times the reciprocal. And that would be the limit as n approaches infinity of n to the fourth plus n cubed plus n squared over n to the fourth plus n squared. I am going to divide by the highest power term of the denominator, make that a 1, plus 1 over n squared, 1 plus 1 over n plus 1 over n squared. Those will zero out. I'll get 1 over 1, which is bigger than 0. Therefore, they both converge by the limit comparison test. Now I'm looking at number 24. Again, I could jump and say, oh, look, the top is dominating by 3 to the n, 2 to the n, and that's actually the series of 3 over 2 to the n. This is geometric. R is bigger than 1. Or I could look at this and say, wait a minute. The top is growing faster than the bottom, which means the limit would be not 0, and therefore it could diverge by test for divergence. You should try that on every problem, right? And in case you've forgotten, let me remind you. This is the order of growth. Order of growth or increasing. Factorials are the fastest growing functions that we have. Exponentials come after, then polynomials, then radicals, and then logs. To undo a very fast function, you need a very slow function. To undo a polynomial, you need a radical, and we do not know how to undo a factorial yet. Now, you could use those for your own benefit to know what the limit is, but you can never quote them. You can never say, well, I'm looking at an exponential divided by a radical, therefore it's going to be, you have to show that. So here, if I take the limit as n approaches infinity, since I know the top is growing faster or at the same rate, here that wasn't the case, right? So you should attempt that on every problem. And if I divide by the highest power term of the, let's just use L'Hopital actually, either way, n plus 3 to the n over n plus 2 to, because if I divide, I'm going to have to show that 2 over 2 to the n approaches 0. I can't say that equals 0. I have to show it. A number over a function that's growing is 0. that's allowed. So if I take the limit that's infinity over infinity by L'Hopital, n approaches infinity, 1 plus 3 to the n times natural log of 3 over 1 plus 2 to the n natural log of 2, that's still infinity over infinity. If I apply L'Hopital again, and every time you apply L'Hopital you have to put that h on, that's 3 to the n times natural log of 3 squared over 2 to the n times natural log of 2 squared. That is the limit as n approaches infinity of 3 halves to the n times natural log of 3 squared over natural log of 2 squared. This is infinity because this is exponential growth. The common, what do you call it? The base is bigger than 1, which doesn't equal to 0, therefore diverge by test for divergence. Alright, we want to look at the next problem. Next problem, number 30. Well, if I figure out that the top is dominated by n factorial and the bottom by n to the n, I could get the limit to equal 1, but I don't know whether that converge or diverge. If I knew, I would know whether this converge or diverge, and I'm done. So that doesn't do me any good. Instead, I'm going to have to compare, and I know, like I said, when we get to chapter 11.6, you will have a way of doing this. I'm going to take the top and break it. That's n minus 1, n minus 2, 3 times 2 times 1. The denominator is a bunch of n's matching. So if I really was to look at this, this is 1. This is really 1 minus 1 over n, so that's less than 1. This is 1 minus 2 over n. 3 over n, 2 over n, 1 over n. So basically, I'm going to use a 1 all the time. I'm going to replace this by 1, this by 1, this by 1, and I'm going to put a 1 for all of them. Actually, all of them except the last. And I have a couple of choices. So I'm going to put a 1 for each of those. This one is for that. This one is for that, and so on. But I notice, if I leave it as 1 over n, this will diverge. I could do comparison any way I like. So I'm going to take another term. And I'm going to say, look, this right here is actually, and I know this is bigger because this is less than 1. I replaced it by 1. This is less than 1 by 1. I replaced it by 1. So I'm making it bigger. Right? And this is 2 over n squared. And this is a p series. Therefore, the series n equal 1 to infinity of n factorial over n to the n converge by the comparison test. On the last problem, use the sum of the first 10 terms. So you plug this in your calculator. And the reason they're using that, well, look, these things are, they're decaying very fast. I'm going to get a value, and that is 0.19788. If you put this in a calculator, it's a very small number. Now they say estimate the error. Isn't the error what I left off? Isn't that the series n equal 11 to infinity of 1 over 3 to the n plus 4 to the n? Wouldn't you say on the side that 3 to the n plus 4 to the n is bigger than, let's say, 4 to the n? Isn't that less than? So you can say this less than or equal the series n equal 11 to infinity of 1 over 4 to the n? Isn't this geometric? And wouldn't that be the very first term divided by 1 minus r? The very first term is 1 over 4 to the 11 over 1 minus 1/4. Or you could say that's less than or equal to the integral from 10 to infinity, 10 you guys, of 1 over 4 to the x dx, and proceed. And there's the homework of that section.